Welcome back once again. This is Dr. P.A.Hagargi from SVERIs College of Engineering. Let me tell you another example on the target code generation for the given 3 address code. Move on. Before that, let me brief you. The intermediate code means the intermediate code, which is nothing but the target code, is another form and which is easy to generate and convert the machine code or the target code. As the intermediate code has at most the 3 addresses and it is nothing but a combination of the assignment and binary operator to represent an expression. Its value computed is stored in temporary variable generated by the compiler. This is why I'm briefing, because today I'm going to deliver another video lecture on the same topic called as the target code generation, and target code generation is all dependent on the intermediate code. A machine can directly generate the target code, but why an intermediate code is required? It is intermediate code is required because to reduce the computation speed and also for the betterment utilization of the memory. Therefore, the target code is required. And the furthermore, the intermediate representation is in two ways. That is the high level intermediate representation and the low level intermediate representation. The high level intermediate code representation is very close to the source language itself, and they can be easily converted from the source code, and we can easily apply the code code and code modification to enhance the performance. But for the target machine, optimization is less preferred. Once the target code is converted, there is no need the modification cannot be done, or the optimization cannot be done in the target code. Why? Because it all depends on the final code generated of the intermediate code. And the another level, which is nothing but the another intermediate code representation, is nothing but the low level intermediate representation. This is close to the target machine. This is very close to the target machine, and which makes it suitable for register and memory allocation. Which makes it suitable for register and memory allocation. Which makes it say once again, listen, dear students, and this is one of the close to the target machine, and which makes it suitable for register and memory allocation, instructions set, selections, etc. And it is good for the machine dependent optimization. As I said, in the high level language, or the high level intermediate code representation, in high level intermediate code representation, optimization code can be modified, but once after the optimization code, from that resultant only the target code is generated, and where the target code cannot be modified, and in the low level intermediate code representation, which itself is very close to the target machine code, and where it makes us very suitable for the register and memory allocation, instruction and the selection, instruction, selection set, and etc. It is good for the machine dependent optimization. Intermediate code can be either a language specific, like say for example in Java, in Java, for the target code we call it as the byte code for the Java, which is a very dependent on its machine, like dependent on the machine, like in the sense, like in Java we have its own language. Java itself is a own language. Like in C and C++, they are machine independent, and they are machine independent languages, and they generate, or they all the target code generation depends on the 3 address code. The target code depends on the three address code. One thing we have come to know from these 2 points, the target code cannot be modified, and the target code is a dependent or machine dependent. Like in Java, a it itself is a in the machine specific, like it is dependent on the language. So the bytecode is the target code for the Java, whereas in other languages the target code is dependent on the language. Now the very specific example which I wanted to tell in the last video, also we have seen the same example, but I want to brief here once again the same example. The target code for the given code is A is equal to B plus C and D is equal to A plus E. Here, how the target code is generated. Here I have a, here I have shown the arrow mark which I would like to track here, how the from the intermediate code. A is equal to, here I have a given code A is equal to B plus C and D is equal to A plus E. For this, intermediate code is generated, and using the 3 address intermediate code, based on that intermediate code, let me tell you here for this given code how the target code is generated. Like target code is nothing but an machine understandable language, or the machine coded language. And this machine coded language, like say for example A is equal to B plus C, load R naught comma B in the sense, in the register R naught we are loading the content or the value of B in register called as R0, and both of them are added with the C. Now where the C is loaded, again the C is loaded with the R0. The previous value of the R0 to that, along with that it is added. Next, now what does it mean? The both the computed value B plus C are computed value, and they are the computed value of the addition, and they are being assigned to the variable, or their computed value is being assigned to the variable called as A. So here we need to store A. And the computed value which is stored in the second instruction R0, which is stored here, the second the value computed is stored in R0, and this R0 is being transferred to or is been stored in uh, the A, is been stored in A. Now here we have the next instruction, that is D is equal to A plus E. D is equal to A plus E. In that, again load R0. Why? Because again we are taking the same register. Why? Because now R0 became free in the first line of the instruction or first given code. Now again I am utilizing the same register, that is the R0. Again A is loaded in R0, and here A is added with E. So how the A is added with E? Whatever the value is stored in in R0, it is being added with E. Whatever the value is stored in R0, it is being added with E. And the added value which is in R0 is being again stored by D. R0 is again stored in D by using the instruction called as ST. So for these two code, how is the target code generation for these two code? How is the target code generation? And this is all because of the intermediate code. Well, we are not able to see here the intermediate code generation, but here the example or this is the video lecture where directly I am just showing you how the how the target code is generated for a given 3 address code. Of course this is a 3 address code, but here there is no any this is a 3 address code, and here there is no any unnecessary steps or unnecessary instructions in the given code. So directly assuming that these are the optimized code, so optimized code directly are fed into the target code. So here they both the b plus c are added. Before addition, the b is loaded in r naught. Sorry, b is loaded in r naught, and whatever the value is in r naught is being added with c. Is been added with c. So in r naught we have the previous value which is computed b plus c, which is holding the value of b plus c. So this r naught value is being assigned to a to store the resultant value of the addition b plus c. In the same way, for the second line of the code, these are the target code generated. So load this a in r naught, and add the value of r naught with e. Add the value of r naught with e. So both of them are added, and so it is the final value computed is stored in r naught. And again in this r naught, and in this r naught, not in this r naught, the value which is holding or the result which is having r naught is being stored in d, this is how the target code generation. And the very next we shall move to the another example. Here we have another example of the target code generation. The target code generation for the assignment what is being given here, d is equal to b minus c, it is taken in the bracket, and we have another expression that is a minus c, and which is added with a minus c, again which is added with a minus c, can be translated into the following sequence of the three address code. So it is t is equal to a minus b, and u is equal to a minus c, and v is equal to t plus u. That is, these both together they are being added and they are being stored in in v, and again further v is being added with u. This is the last one. Again further v is added with, let me take here down. This is how it looks like, can be translated into the three address code. This is how the translated three address code. This is how the translated three address code. The we have here a given expression, and this can be translated into the following sequence. But see, it's still here I haven't shown how does it generate the target code. Well, we are seeing here the three address code. This is a little bit blur videos, where for this how it generates the three address code. First, move into r naught the value of a, or the variable is moved into r naught. Here we are going from left to right. Move in r naught the a, move in r naught the a. Then what I have told here, move in r naught e a, the r naught contains the value called as t. R naught contains the value called as t. Now how is the address descriptor? T in R naught. T in R naught. T in, where T is in R naught. Here this for the first expression, that is T is equal to A minus B. Now next what we need to do is for this the A minus B we need to subtract. So how we need to subtract? Subtract B from R naught. Subtract B from R naught. What R naught is holding? R naught is holding the value of A. subtract b from r0. This is how the target code. And next another expression, that is a minus c. Again in the same fashion, move a into r1, move a into r1, as r0 contains at t and r1 contains at u. So in the address, how the address descriptor look, t in r0 whereas u in r1, t in r0 whereas u in r0. Now another, v is equal to t plus u, v is equal to t plus u, add. Now again in the same way, I have taken these two should be added. I mean these two expressions should be added. So add directly the r1 and r0. Directly add the r1 and r0. So r0 contains at v and r1 contains the value u. So u in r1 and v in, sorry, u in r0, u in sorry u in r1 and v in r0. It should be v in r0. Next, d is equal to u plus v, where this is the last part of the expression. In the previous slide we have seen, that is plus, it is added with a minus c. It is added with a minus c. Again, as a minus b is d and a minus c is another u, and v is these two edited value, t plus u, t plus u. Again this is added with v, holding v, till here it is holding v, and v is being added with u, a minus c, and v is being added with a minus c, this a minus c. So in the same way, here also I am taking. So here I am describing here in this manner. So d is equal to u plus v. So u plus v, again what was previously holding here, this was holding r0 and again we are considering in the same way, r0 and r1, r0 and r1, add r0 and r1. What r0 was having, r0 was having the whole content of this, and r1 was having the whole content of a minus b. So r0 contains d, and d in r0 and d in r0 and memory, d in r0 and memory. From the memory we are picking, from the memory we are picking. This is how the example of the 3 address code, sorry, this is how the generation of the target code. Now once again briefing you, the 3 address code, which is a intermediate code generation, receives the input from its preceders phase semantic analyzer in the form of an annotated syntax tree, and that syntax tree then can be converted into linear representation, that is postfix notation. Intermediate code tends to be machine independent code, therefore code generator assumes to have unlimited number of memory storage register to generate code. For example, a is equal to b plus c star, and the intermediate code generator will try to divide this expression into sub expression and then generate the corresponding code, like in the previous example also, how we were converting the intermediate code into division of the expressions into subdivisions of the expressions. Now here also b plus c, before that c star d, which is nothing but multiplication, is stored in r1 and holded in the variable called as the r1 and r2. R1 and b2, these two are added, and the computed value is being assigned to A, where R being used as the register in the target program, where R being used as the register in the target program. As we know, the 3 address code at most has the 3 address locations to calculate the expressions. A 3 address code can be represented in two forms, that is quadruple and triple. Quadruple and triples. This I have told in my last video also. We have covered a detailed discussion on the intermediate code generation using the 3 address code. So we have seen lot more examples on the target, I mean intermediate code. So this is how the another example which I have taken here, how the intermediate code, I mean what I mean to say here is how the intermediate code makes them again the further subdivisions of the expressions, sub expressions, and then go for the generation of the target code, and then go for the representing the target code. It becomes very easy for because as the temporary variables holding very importance in the registration, so that they can, I mean as the temporary variables being used as the register in the target program, and this makes very easy conversion of the target code from the sub expressions. The whole, because sometimes the expression may be very lengthy, and how the machine converts them into sub expressions and later go for the target code. So in this video we have learnt about another example on the target code generation. So how it does the target code holding holding the registers, and before going to the target code directly conversions, it makes itself very easy for the subdivision expressions. Then it goes for the conversion of the target code generation. This is how we have seen here in this video. Thank you.